about this work with my two co-authors, Tyler Sorensen and John Wickerson of Imperial College London. Our work's about two key characters, transactions and weak memory. And they're interesting characters to consider together because they differ in how they want to treat you as a programmer. Transactions, they want to make your life simpler. They say, forget about fine-grained locking, gather your program up into a collection of transactions, and I'll promise you atomicity, meaning a transaction wholly executes or not at all, and isolation, meaning you can reason about the execution of a transaction as if there were no interference from other threads. So transactions are an appealing form of optimistic concurrency that promises scalable performance without programmer pain. On the other hand, weak memory, if not making your life harder, then at the very least is saying you have to be aware of what's going on underneath, in the machine. Caching, buffering, out-of-order execution. These are all micro-architectural techniques that break the programmer intuition of an interleave semantics. Despite these differences, it's important we consider these two together because modern architectures and languages have a weak memory semantics and specify or have transactional extensions. This is the case for x86 and Power. C++ has a draft technical specification. And inside ARM research, we have also been considering how transactions would affect the ARM architecture. So this is the underlying motivation for our work. And in our paper, what we've tried to do is clarify the interplay between these two characters for real-world architectures using rigorous semantics and automated tooling. And we've discovered a number of interesting ambiguities and counterexamples by doing this. I would like to talk about the first of these in the remainder of this talk, which is the unsoundness of lock elision with respect to a particular ARM v8 Spinlock. And what I find particularly interesting about this counterexample is that individually, both of these characters are safe, but their naive composition, as we shall see, is not. So our automated tooling is built on top of the memalloy tool from Wickerson and others. And if we feed in an axiomatic model of our ARM v8 semantics plus our hypothetical transactional extension, along with the idea of lock elision and this spin lock, which I will explain shortly, then we can ask memalloy if the crucial correctness condition of mutual exclusion is preserved. And it comes up with this counterexample on the right-hand side. In more standard notation, the counterexample is this. It's a program consisting of two threads with a single shared variable, v, initially 0, and two critical regions, and hence two possible serializations. Left followed by right, in which case v should be 1, and the other way around, in which case v should be 3. What would be surprising would be a final result of 2, because this would imply that the critical regions have overlapped. And this, of course, is precisely what a critical region should not do. So in order to fully explain this counterexample, I'm going to need to lower it into ARM assembly. Let's start with the critical regions themselves. V becomes v plus 2. Well, that's just a load, an add, and a store, so long as we agree about where we've placed the address of v. Let's put in x0. And similarly for the right-hand side. Now we can turn to the meatier issue of how we'll handle the lock and unlock procedures. Let's use our first character, transactions, and let's use what is considered to be one of the killer applications of transactions, lock elision. This is a beautiful idea by Rajwa and Goodman, and their chief observation is that if you have a set of critical regions and they turn out to be dynamically disjoint, then the serialization caused by successive locking and unlocking is unnecessary. So the idea then is to try to recover this lost performance by eliding or skipping taking the lock. And instead, we'll execute the critical region inside some speculative mechanism that allows conflicts to be caught dynamically and serialization to be enforced only when necessary. So you can see why transactions are a good fit for this idea. There's only one subtlety with this, which is this if statement. This is ensuring that the lock variable is free when we're doing this speculation. Imagine that we have a critical region that is executing speculatively in this way. And now imagine that another entity really acquires the lock by writing to the lock variable. Then the conflict on the lock variable will force this speculative critical region to be aborted. Jumping up a level, the reason for this is because hardware transactional memory systems are best efforts. This means there's no guarantee of forward progress. There must always be a software fallback, such as taking the lock variable. So it's important that we have this if statement for the correctness underneath this mixing of critical regions executed speculatively like this and critical regions that happen to fall back to taking the lock. Back to our program, and let's apply lock elision to the right-hand side, including this important if statement. And further, let's lower it into some ARM assembly, at which point I will point out again that the transactional instructions that we have on here are really just for a research prototype that we're considering. There are no transactional extensions inside ARM v8. On the left-hand side, let's use our other character, weak memory. And let's use a Spinlock that we can find inside the ARM architecture reference manual. Now, Spinlocks in real applications are, of course, much more complicated than this. But this is still an interesting implementation because it contains a number of weak memory effects, and it contains the essence of more complicated locks. So, of course, the goal is to atomically update the lock variable from free to taken. And the heart of this is this pair of exclusive instructions, the load exclusive and store exclusive, which you can consider to be the RISC alternative to a compare and swap operation. The load exclusive, it reads from the lock variable, and it sets a monitor that's going to watch the location for any updates. When the store exclusive attempts to update the location from 0 to 1, one of two outcomes can occur. Either there has not been an intervening write in between the time of the load exclusive and the store exclusive, in which case the store exclusive can succeed, and the update occurs, or the store exclusive fails and the update does not occur. Either way, the status of the store exclusive is returned inside this W4 register, which we can test. Sarkar and others studied the analog of exclusives for the power architecture, and I like their explanation too. They say that the write of a successful store exclusive, which we denote by putting it inside this read, modify, write relation, must be the immediate coherent successor of the write read from by the load exclusive. In other words, for the update to be atomic, there must not be any intervening writes to the lock location. This is a spin lock, so there are two ways that we need to consider retrying taking the lock. This is if the lock is already taken, and secondly, if we fail to take the lock atomically. This would be the case where we have two or multiple instances of this spin lock attempting to take the lock. They're racing to become the immediate coherent successor. At most, one can succeed, and the others are going to have to retry. Unlocking is simple. All we have to do is write 0 to the lock variable. And finally, and to foreshadow what is to come, most importantly, we have these acquire and release semantics added to the load exclusive of the lock and the store of the unlock. And informally, you can think of the acquire and release as being half barriers. They're barriers in the sense that they delimit the scope of the critical region, the top and the bottom. But they're half barriers because they only forbid reordering one way. So we're allowed to grow the critical region. We can make it larger by moving things into it, but we're not allowed to hoist above the acquire or below the release. More formally, you can say that a read exclusive is ordered before, where order before is a relation that all agents in the system will agree on, any program order successor, and analogously for the store exclusive. Back to the program, and let's put in our Spinlock on the left-hand side. And let's remind ourselves what we were trying to do. We started out with this program in the top left, and I've gradually lowered it into ARM assembly. One way of thinking about this lowering is that we've applied lock elision, the idea of lock elision, and dynamically it's turned out that the left-hand side has failed to execute transactionally and now is going to fall back to acquiring the lock. And the right-hand side is going to continue to use lock elision. And the key question is whether we can get a legal behavior of this program resulting in V being 2, i.e., showing us or indicating that our critical regions have overlapped. So in other words, we have a play that is ready for our two characters. Let's imagine that V is 0 and the lock is free. The first thing we'll execute is the load acquire exclusive on the left-hand side. This reads the lock as being free, which means that we can fall through the branch. But also, you might want to set that monitor inside your head that's going to be watching the lock location for any intervening writes. At this point in time, you may think that the only things that can be executed now are the T-start, the transaction start on the right-hand side, or the store exclusive. It turns out there's another behavior that's allowed. It's the load of V as part of the critical region. This is quite subtle and surprising, so I'm going to say it again. We're going to start executing the load of the critical region before we have acquired the lock. So firstly, why is this legal? Well, notice that the acquire semantics are on the load exclusive. So we're certainly not allowed to hoist above that. But these acquire semantics are not inherited by the store exclusive. So there's nothing prohibiting us from hoisting in between them. Secondly, is this safe? Well, yes, if we're using this Spinlock implementation against itself. Imagine that we had two such critical regions that had reached this point. They've both read the lock as being free, and they've both started to execute their critical regions speculatively. Well, now there is a race between their respective store exclusives. Recall that for a store exclusive to be successful, its write must be the immediate coherent successor. There can only be one of those, and so the side that loses will have to squash its speculation. So this is the reason why this Spinlock implementation, when it's against itself, is indeed safe. It is the semantics of exclusives that guarantees this. Even though it might appear strange that we're allowed to execute the critical region before actually acquiring the lock. Now, let us try and interleave the critical regions, which means we have to jump over to the right-hand side. Let's start the transaction and read from the lock variable. It's free, so we can jump to the critical region. We do the store to V of 1. Of course, this does not occur immediately because we're inside a transaction. This will be buffered until we're able to commit the transaction successfully. But we really have run this transaction in isolation. There are no data races or conflicts on the lock or on V. So let's commit this transaction and update V being 1. At this point in time, the counterexample should be collapsing in on itself, and you can see how this story is going to turn out. All we have to do is ensure that this store exclusive can be successful. But of course it can be successful because there hasn't been an intervening write to the lock variable in between the time that we did the load exclusive in step 1 and now. Of course there hasn't, because this is the point of lock elision. The point of lock elision is to elide or skip writing to the lock variable. So now the store exclusive has succeeded, which justifies the earlier speculation that we did of that critical region. All that remains to do is to tie up the loose ends. Notice that W5 contains the stale value of V now. We're going to lose the update of V being 1. We write 2 back to V, and we release the lock. And therefore, we've shown a legal behavior of this program that shows a violation of mutual exclusion. Looking back, it's interesting to note that individually, both of these characters were sound. I had an argument for why this load-exclusive acquire Spinlock was safe in isolation. And of course, the semantics of transactions, if we had a purely transactional world, the isolation property of transactions would guarantee serialization one way or the other. It is their combination that is unsound, and what is so particularly interesting is the fact that the thing that makes the load acquire exclusive sound, the fact that you must write to the lock variable, is the very characteristic that lock elision is performing. Rajwa and Goodman had this to say in their paper. I think they were almost right. I think they had a vital assumption that they did not make explicit, which is that the lock acquisition must always happen before any memory access of the critical region. And this is a reasonable assumption, because in 2001, a load acquire exclusive Spinlock wasn't possible. ARM only introduced this instruction in 2011 as part of the V8 architecture. So depending on how you count this, this is a 7 or 17-year-old counterexample. The fix, of course, is to make sure that that assumption really is guaranteed. And there are a number of ways that we could do that. Most easily by putting in a barrier in just the right slot between lock acquisition and the critical region. To jump up now and stop talking about this counterexample, I'd just like to call attention to a few key ideas that we've used in our work. In particular, the work of Wickerson, Lustig, and others, which have given us techniques in our automated tooling for producing just the right tests, for producing or for testing the empirical soundness and completeness of our models. And I'll also point out this highly related piece of related work at Popple this year by Brijesh Dongal and others, who have tried to tackle the same problem, but where we have been looking at the interaction for specific architectures, they have been looking at general transactional extensions. And so our work is very complementary. In summary, our work is a step towards a better understanding of the interplay between these two characters. And we've done this for real-world architectures using rigorous semantics and automated tooling. And we've used these to look at the empirical soundness and completeness of our x86 and power models, and also for the bounded verification of key properties, such as the compilation of C++ transactions into architectural transactions. And the counterexample I've shown you demonstrates that a naive composition of these two is unsound for this particular ARM v8 Spinlock, thus underscoring once again the need for rigorous semantics to help us understand these complex machines that we design and build. Thank you.
Questions?
I want to confirm that I'm understanding, a point that I don't think you made explicitly. Mm-hmm. At one level, I would say you compared two different lock implementations. And so, if this lock implementation assumes one is locked and 0 is unlocked, and this one assumes the other, then of course they don't, establish any mutual exclusion. So am I really to understand this as, think of the Spinlock as the software fallback of the lock elision, and we just happen to be in the situation where, it's a combined implementation. One is still executing the lock elision version, and the other one has already fallen to the software fallback, and that's where the interaction is happening.
That's right, yes. As I said, you might consider it as that program undertook lock elision. We failed on the left-hand side and fallen back to the Spinlock.
Okay.
But our designer of the Spinlock didn't realize that it was going to be used in this elision case. And hence the naive composition can lead to this unsoundness.
Okay, thanks.
First, thanks really a lot for forcing the slow walkthrough of that example. Really great.
Thank you.
It occurs to me that there could be trilock implementations that are equally broken. Have you found any?
So we've only looked at very simple spin locks for each of the architectures that we've looked at. We've not looked beyond that. Potentially, they too suffer from the same issue of being able to execute the critical region early, in which case that would be the thing that you would look out for.
Right. Also a note, maybe you've already noted this. This is basically the same bug as the C-clock bug reported by Hans Bohm a few years ago.
Oh, is it? Okay, I didn't realize that. I guess I'll have to track him down.
Yeah, you need the same fence for the same reason.
Right.
We have a few minutes, so I'm just going to ask a question on the rest of the paper. Could you summarize what is the simplification to C++ TM specification?
Yes, sure. I'll see most of the details to John, who's in the front here, who worked mostly on this part of the paper. But I believe the simplification that we proposed is that the original specification had a total order over all transactions, and we noticed that we could encode it in a partial ordering instead and still have the same semantics. Okay. That was the main contribution that we made to the simplification.
Thank you. Okay, let's thank the speaker.